Chapter 23 is all about amines. Amines are interesting compounds, they are smelly compounds, and there are a lot of topics that we have to cover when we talk about amines. So let's get started. First of all, what is an amine? Well, an amine is a compound that has nitrogen and usually a hydrogen and some carbons on it. We classify the amines into three different categories. The amines are primary amines, where we have either one alkyl or aryl group on it, a secondary amine, where we have two of those groups, and a tertiary amine, which has three of those groups. And so those are the ways that we classify them. We'll find that amines are stronger bases and better nucleophiles than other neutral organic compounds. And when I say this, I'm talking about neutral organic compounds in period 2. So more so than nitrogen, or more so than oxygen or fluorine. All right. When we get to period 3, we get some weird stuff. So we'll just say more so than other atoms in period 2 that are neutral. We're going to find that amines are both basic and nucleophilic. So ammonia, which is similar to amine but a little bit different, the amine nitrogen has a non-bonded pair of electrons that can act as both a base and as a nucleophile. If it acts as a base, it will get deprotonated. It will deprotonate an acid, and in doing so, we will generate an ammonium salt, and that's what we have here. But we can also react nitrogens with electrophiles, so for example, like alkyl halides, and when we do that, we can get quaternary ammonium salts, which those are interesting in their own right. Now, we're not going to talk a lot about the quaternary salts. We're going to talk mostly about primary, secondary, and tertiary amines, but we will briefly mention the quaternary ammonium salts. Let's look briefly at the structure of amines. The nitrogen is sp3 hybridized. It consists of 3 bonds and a lone pair of electrons. Typical carbon bond strengths come in at about 1.5 angstroms, or 147, if we're going to be more precise there, 147 picometers. And the angle, because it is trigonal pyramidal, we have a tetrahedral electron arrangement around the nitrogen, is going to come out close to the 109.5. In this particular example, trimethylamine, it comes out at 108. That's pretty typical for a lot of our amines. We'll find that both methylamine and trimethylamine have electron-rich regions. Those electron-rich regions are where they act as bases and or nucleophiles. Can amines have stereogenic centers? The answer to that is yes, they can have stereogenic centers. So an amine nitrogen is bonded to 4 different things, a lone pair of electrons, and potentially 3 different alkyl groups or a hydrogen. And if that is the case, then yes, technically it has a stereogenic center. If there's 4 different things attached, it is a stereogenic center. However, for most of these amines, it is not possible to isolate the different enantiomers. So if we had this amine and we tried to isolate this particular one and separate it from this enantiomer, we would find that that would be impossible. And the reason is that the one enantiomer will easily interconvert into the other one. And there's not really much we can do about it. It's going to happen even at room temperature. Even at pretty cool temperatures, we will find that this happens. So for the most part, we generally ignore nitrogens as amines as stereogenic centers. However, a caveat, ammonium salts can have stereogenic centers that don't interconvert on their own. And that's because if we have 4 different things attached and one of them is not a lone pair, then it is definitely possible that we could get a chiral ammonium salt. In this case, we have 4 different things include 3 different alkyl groups and a hydrogen. We could potentially have 4 different alkyl groups that would be classified as a stereogenic center. So in this case, we can't really ignore it. Again, we're not going to talk about this in any great detail. We're going to stick mostly with looking at amines, not so much the ammonium salts. All right, we're on the nomenclature section, and the nomenclature for amines, it can be a little bit confusing because we have systematic names, the IUPAC names, and we also have common names that are so commonly used that we really need to know those as well. So if you're going to do the systematic name, you need to find the longest continuous chain, the longest alkane, and change the ending from E to amine. So for example, methane would become methanamine, and cyclohexane would become cyclohexanamine. For the common names, it's actually a little bit easier, and this is in many cases more often used. This is wherever the nitrogen is, you just say what the alkyl group that is attached to it, and then slap the word amine on the end and make it all one word. And so this is a methyl group, so we call this methylamine. This is a cyclohexyl group, so we call this cyclohexylamine. We're going to find that these names are so commonly used that in many cases they're more commonly used than the IUPAC name. In fact, in probably most cases. I'm not sure that I know anyone who uses the word methanamine, but I'm sure there are people who call it methanamine, but most of the chemists that I know call it methylamine. When it comes to secondary and tertiary amines, we just add the prefixes di and tri to indicate how many of those alkyl groups if they're the same. So for example, this amine has 3 ethyl groups, so we call it triethylamine. This amine, which we've seen before, it has 2 isopropyl groups, so we call it diisopropyl amine. If we have different alkyl groups, we're usually going to resort to we're generally going to resort to the systematic names. So for secondary and tertiary amines that have more, we're going to call them N-substituted primary amines, and we'll use this procedure. So we'll find the longest chain that contains, or the largest ring, so the longest chain, largest ring that is bonded to the nitrogen, and we're going to call that the parent amine using our systematic nomenclature. So for example, here we've got 3 carbons, it's bonded to the second carbon, so we would call this propan-2 amine. If this were NH2, that would be the end of that name. We have a methyl on there, and so for the substituents that are on the nitrogen, we're going to indicate what those are. We will alphabetize them, so we'll put them in alphabetical order, and we'll give the prefix N before the name. We did this prefix N when we were talking about amides in an earlier chapter, and so here this will make sense. We will use that in this case. So here we've got the example propan-2 amine, and we have a methyl on the end, so on the nitrogen, so we call it N-methyl propan-2 amine. Now, this is one of those things that was changed in the 1993 change in nomenclature. Before then, most chemists called it 2-propanamine, and in that case, there's a lot of textbooks that sometimes still have that old nomenclature in it, so just kind of be aware of that. And you might also, if you find older chemists, you might find them using the old nomenclature as well. When it comes to aromatic or other amines, If we have a benzene ring attached to an NH2 group, we call that aniline. Now, we've seen aniline before when we were talking about aromatic compounds. So aniline has come up a number of times. So you should be familiar with that name. And then as far as any substituents that are attached to it, if they're attached to the nitrogen, we would just put them in front. If there's more than one substituent, we would capitalize them. And then here we have a substituent on aniline on the benzene ring, and so we could call this ortho-bromoaniline, or we could call it 2-bromoaniline if that suited you. If we have an NH2 group, like let's say something else has higher priority as far as the naming, then we will call that NH2 group an amino group on some other compound. All right. When it comes to nitrogen heterocycles, there are quite a few of them, and so this is just a small sampling of them. Pyridine, we've seen pyridine before. This was particularly useful when we were doing reactions with acid chlorides. This is pyrimidine. It has 2 nitrogens in the 1 and 3 position. This one is pyrrolidine, which is it's a 5-membered ring, no double bonds in it. This one is pyrrole, which has a 5-membered ring, but we have 2 double bonds, and then that lone pair on the nitrogen, that makes this an aromatic compound. It follows that 4n plus 2 pi electrons. Go back to the chapter on aromatic compounds if you have any doubt about pyrrole. And then purine is a very interesting compound because it's a very interesting base because it has, there are lots and lots of other compounds that are based on purine, some including, let's see, not nicotine. Nicotine has a different shape to it. Caffeine. I was thinking of the wrong stimulant. So caffeine is a purine derivative. It has this structure to it. So let's look at number 37 on our in-class assignment. So we'll switch over. I'm going to look at this and so give a systematic name for each of these compounds. And we can give a common name if that is more appropriate. I'm going to stick to the systematic nomenclature. So here, our longest chain is this 4-carbon chain here. So I'm going to put 1, 2, 3, 4. You always put carbon 1 is the one that is attached to the nitrogen. And then when you do that, or carbon 1 is the one that's attached to the nitrogen if it's at the end. If it's in the middle, you want to make the carbon that's attached to the nitrogen have the lowest possible number. So in this case, it's 1. If it were in the middle, it would be a 2 or 3 or something like that. So here on this one, we've got that. So that's butane. And so this we would call our butan 1 amine. So butan 1 amine. And now we'll look at the things that are attached to it. We've got a methyl at the 2 position. So this is a 2-methyl group. And we've got on the nitrogen, we have an ethyl group. And so that we will call an N-ethyl. All right. Well, we're going to put the N's out first. So we'll put N-ethyl 2-methyl butan 1 amine. And that is the name of that particular compound. I'm trying to think if there's anything else somebody might call that. That's probably the best way to name that one. I don't know if there is a common name for this. I haven't looked it up to see if there is. All right, here we're going to find our longest chain, and clearly it's going to start there. 1, 2, 3, 4. If we go here, that'd be 5, 6. Go here, 5, 6, 7, 8. So 5, 6, 7, 8. So that means we have an octan 1 amine. Interesting. I don't think I chose. Oh, yes. Here I've got one that is. Here I've got one that is in a longer group. So, all right. So we've got that. So we've got an octan 1 amine. At the 2 position, we have a methyl. And at the 4 position, we have an ethyl. So when we put that all together, we'll put these in alphabetical order, and that will give us 4 ethyl, 2 methyl, octan, get rid of that A there, and then we'll put 1 amine. All right, so that is the name of that particular structure. On this one, we've got a cyclohexanamine. All right, on this, we don't need to indicate that it is at position 1. It is assumed to be at position 1. And since we don't have any other substituents on that cyclohexyl group, then it doesn't really matter what position it is at. We have on the N, we have a methyl group here. And there we have an ethyl group. All right, so we're going to put these separately, and we will put them in alphabetical order. So ethyl will go before methyl. So we'll have N, ethyl, N, methyl, cyclohexanamine. So cyclohexanamine. All right, on this particular one, we're going to use aniline as our base. So this is the parent, and so that is called aniline. And then attached to that, we have an ethyl on the N, so we'll call that an N-ethyl. And here we've got a tert-butyl, so we'll call that an N. Tert-butyl, and we're going to put those in alphabetical order. Remember, we don't include tert as part of our alphabetizing, so we're going to put butyl before ethyl. So this will be N, tert-butyl, N, ethyl, aniline. All right, on this one, our higher priority is going to be the cyclohexanone, so the carbonyl. And so this is a case where we have an amino group on a different kind of compound. So our parent is cyclohexanone. All right. And as far as numbering goes, the cyclohexanone is going to be carbon 1, 2, 3, and then 4 will be for the amino group. So we have a 4 amino. And that's pretty much it. So we'll just throw all that together, and we'll get 4 amino cyclohexanone. So 4 amino cyclohexanone. All right, so in this case, we've got our parent, and I'm going to go ahead and circle that parent in green. So this is our parent, and that parent we call pyrrolidine. All right, so two R's to P-Y-R-R. I got a little sloppy there. So P-Y-R-R-O-L-I-D-I-N-E, pyrrolidine. All right, and on that pyrrolidine, we're going to call this carbon, or not carbon 1, but position 1, and that we have on the 2 position, we have an ethyl. So we'll call that 2-ethyl. And so when we have heterocycles like this, we include the nitrogens as part of the numbering system. And we saw that with purine a little bit earlier. All right, so we'll put that together and call it 2-ethyl Pyrrolidine. So 2-ethyl pyrrolidine. And that's all one word. There's no space there. All right, on this one is an example where we have a nitrogen that is not at the end of the chain. And so this is where we're going to need to number this to give that nitrogen the lowest possible number. So 1, 2, 3. So the nitrogen is at carbon 3, 4, 5, 6, 7, 8. All right, so 8 gives us octanamine, but it's at the 3 position, so we're going to call this octan 3 amine. So that includes that basic structure. At the 2 position and the 4 position, we have methyls. So 2,4-dimethyl. So 2,4-dimethyl. And then on the nitrogen, we have an ethyl. So we'll call that N-ethyl. So we're going to put that N-ethyl out front. So N-ethyl 2,4 dimethyl octan 3 amine. All right, so long name there, but that seems to take care of that one. All right, on this one, our parent is this cyclohexanamine, which is that. And then we just need to look at what is attached. So we're going to call this carbon 1, 2, 3 to give that isopropyl group the lowest possible number. And then the tert-butyl group is on the nitrogen. So we'll call this cyclohexanamine. So that's the parent. And then at the 3 position, we have the isopropyl. So we have a 3 isopropyl. So 3 isopropyl. And then on the nitrogen, we have a tert-butyl. All right, so when we put that all together, this is going to be a really long name. We'll have N-tert-butyl 3 isopropyl cyclohexanamine. All right, I almost ran out of paper there. So, all right, that is how we do the nomenclature for this. I recommend doing some practice on these as we have gone through all these nomenclature rules over many, many chapters. You'll find that trying practice and trying different things and asking questions like, well, what if we did this? What if we did that? And seeing what you come up with. All right, so now let's talk about physical and spectroscopic properties. We're going to start with the physical properties. Because all of these things are polar, every single amine is going to have polar bonds. The carbon-nitrogen bonds are polar. If there are nitrogen-hydrogen bonds, those are also polar. In addition to having dipole-dipole interactions that we get from these, we can also get intermolecular hydrogen bonding with primary and secondary amines because of the nitrogen-hydrogen bonds. So we will get hydrogen bonding, and since hydrogen bonding is a stronger interaction than the regular dipole, we'll find that these are relatively strong. However, we'll find that nitrogen is less electronegative than oxygen, so our hydrogen bonds are a little bit weaker than the ones we get with, for example, alcohols. So our hydrogen bonds are a little weaker, meaning that our boiling points won't be as elevated as we'll have for an alcohol. So here, if we compare this tertiary amine to this primary amine, the primary amine is definitely going to have a higher boiling point because of the hydrogen bonding. So you'll see that these are constitutional isomers of each other, but the one with the hydrogen bonding has a significantly higher boiling point. But when we compare that to a very similar sized alcohol, this butanol, we will find that the boiling point for that is much higher because of the intermolecular hydrogen bonding is much stronger. The OH hydrogen bonding is stronger than the NH hydrogen bonding, generally speaking. Okay, so now let's look at number 4. So we'll switch back over here to number 4. All right, we want to arrange these in order of increasing boiling point. And when we're doing this, we also want to state why. And because, I mean, we could put them in order, and if you just guess why, then that would be wrong. This one is going to this one will have the highest boiling point, and this one will have the lowest, which of course this one means this one's in the middle. All right. Now, why? Well, this one has only the London dispersion forces. All right. With only those London dispersion forces, it does have attractive forces between other molecules of that same type, but they're going to be weaker than the other interactions, which include this one, which has dipole-dipole. I mean, it has London forces, but it also has the dipole-dipole interactions. All right. Dipole-dipole is going to be stronger than just the London forces alone, so this will have a higher boiling point than this. And then this one will have the highest boiling point because it has hydrogen bonding. And with that hydrogen bonding, that is going to give that the highest possible boiling point. All right, so we'll switch back over here. We want to look briefly at spectroscopy for amines. And there's a couple of interesting things. So we have talked about these 3 topics. So we talked about mass spec. We're not going to talk about any mass spec here, but if you go back and look in the Spectroscopy A chapter, you will see the information about mass spec and how you can break bonds adjacent to the nitrogen and all that stuff. So IR spectra and NMR, we're going to look at that. And so here we have a couple of things to mention. The most distinctive peak for amines in the infrared is going to be the nitrogen-hydrogen stretching frequency or stretching absorption. That wave number comes in from 3,300 to 3,500 reciprocal centimeters, and it will be either 1 or 2 peaks. I will talk about this, the 1 or 2 peaks here, on the next page. For the proton NMR, the hydrogens that are on nitrogens are kind of like the hydrogens that are on alcohols. Those particular hydrogens are going to absorb from about half of a part per million up to about 5 parts per million. They are typically broad, and it's not uncommon to not have coupling between this hydrogen and adjacent hydrogens because of hydrogen bonding. So these, in some respects, will act like alcohol hydrogens. And then if for the hydrogens that are on carbons that are attached to the nitrogen, they will have a chemical shift somewhere in the 2.3 to 3 range. Compare that to oxygens, where it's more like, it's more like 3 to 3.5, sometimes even up to almost 4 for oxygens. So because the nitrogen is not quite as electronegative as the oxygen, this number isn't as far downfield. And then as far as the carbons that are directly attached to the nitrogens, those are going to have chemical shifts typically in the 30 to 50 parts per million in the carbon-13 NMR spectrum. All right, so this is something interesting, and I mentioned this on the other page when I was talking about the 1 or 2 peaks. So when you have a primary amine and you look at 3,300 to 3,500, well, first of all, that absorption is going to look very different than we get for an alcohol. If it's a primary amine, so alcohols, as you recall, are much broader. They go from about 3,600 to 3,200, and they're usually a very, very broad and intense peak. For the NH, it is not as intense and typically not as broad. And if you have a primary hydrogen, you'll get 2 absorptions in that region. For a secondary hydrogen, you only get 1. The reason for this difference is when you have 2 hydrogens, there are 2 vibrational modes that these hydrogens can have. There's one that's called symmetric stretching, where the nitrogen-hydrogen bonds are stretching at the same time. And there's a mode called asymmetric stretching, where one nitrogen is stretching while the other one is compressed, and they go back and forth. So symmetric and asymmetric stretching is what accounts for this. We see this in a lot of different scenarios where we have like duplicate kinds of bonding interactions. So it happens with nitro groups. It happens with dicarbonyl groups sometimes. So you'll see this quite a bit, and this is the case that happens here. So with the secondary amine, we only have the 1 hydrogen, so we only get 1 peak because there's no symmetric and asymmetric stretching. For tertiary amines, we don't have that hydrogen, so we don't have this absorbance. So we don't have any absorbance there in that 3,500 to 3,300 range. This is a key diagnostic way that you can distinguish between a primary, secondary, and tertiary amines. Now, there are other ways to do that. There are reactions that happen with primary amines that don't happen with secondary amines, and ones that happen with primary and secondary that just don't happen with tertiary. So there are other ways to do it, but this is a very quick and easy way to distinguish between these without having to actually do any chemical reactions. So I like this one. All right, so let's look at our interesting and useful amines. Some of these are more interesting than they are useful, and some of them are more useful than maybe they are interesting. I guess that's how that always works. But we will find that there are a lot of low molecular weight amines that have some pretty foul odors. If you probably have smelled ammonia, and ammonia has a very distinctive odor to it, and there is a related kind of odor that the amines have. Now, it is different than just ammonia, but to an untrained nose, you may not be able to tell the difference between like a methylamine and ammonia, but if you are around it enough, you will start to notice a difference. Trimethylamine has a very distinctive odor to it. So trimethylamine, when fish start to break down, so like if you have fish that are rotting, there is a very fishy smell that comes out of that. And one of the components that makes up that very foul odor is trimethylamine. And so if you ever open a bottle of trimethylamine in a laboratory, you can very carefully waft some of the vapors to your nose. I wouldn't stick my nose right over it and take a big whiff. that will be unpleasant. But if you waft it carefully, you will be able to get the odor of the trimethylamine and go, yes, I recognize that odor. There are some other compounds that show up when you have either rotting fish or, as you can see down here, various bodily fluids and such that are very unpleasant odors. And in fact, amines make up a significant component of body odor. Now, there are other things. There are some carboxylic acids that get involved, but amines can make up some pretty nasty smells. So putrescine and cadaverine, just the names like putrid, putrescine, and cadaverine, those are things that show up when things start to rot or decay. And when that happens, oh my goodness, these are pretty foul smelling. So it's not uncommon when you smell amines that you think, wow, that smells really, really uncomfortable or really, really unpleasant. Now, there are lots of amines that are much, much larger that don't really have a particular odor to them. And the ones, amines that we can get from plant sources, we're going to call alkaloids. And so these are just amine-containing or nitrogen-containing compounds. We're going to look at a couple of these, but there are countless numbers of these. I don't know how many have been isolated, but I'm sure it's tens of thousands, maybe hundreds of thousands have been isolated. And some of them are very, very interesting. So we've talked in previous chapters about quinine, which is used as a treatment for malaria. My brain stopped there for a second. It's used as a treatment for malaria. Morphine, which comes from the poppy plant, can be used as a painkiller, and there are derivatives of morphine, like heroin that we talked about previously. And also, if you go back to chapter 20 at the very beginning, there was a mention of cocaine. Cocaine is an alkaloid, a very addictive compound. So here are some other common alkaloids. These all happen to come from a family of plants that are called nightshades. Now, not all nightshades produce nasty chemicals that can't be eaten, but and I'll mention this. There are plenty of nightshades that are edible plants, like potatoes and tomatoes and eggplants. Those all fit into the nightshade family, but there's a particular plant that people often call nightshade, even though it's in the nightshade family, and it's more accurately called, well, by its scientific name, I'm not sure of the pronunciation, but the Atropa belladonna. It is called deadly nightshade. And so when people talk about the poisonous nightshade, they're talking about this particular plant. And one of the compounds that is particularly dangerous in that is called atropine. Now, atropine in small doses can be a very potent medicine, but in very large doses, it can be quite deadly. So it's just something that you have to be aware of. Now, also in the nightshade family is tobacco. There's a whole subcategory of, and I don't know if it's a subfamily or a genus or whatever, but there's a whole subcategory of plants that are tobacco plants that are related to this. And so in the one that we're most used to, it has nicotine in it. And that nicotine, as you probably know, is quite addictive. In large doses, it is very, very poisonous. So it's very, very toxic and can be deadly. In small doses, which people usually get by either burning the plant or chewing on the plant, or chewing up dried leaves of the plant or whatever, you can extract this either into your mouth if you're chewing on it, which I've always found kind of gross, or you can extract into your lungs if you're smoking it, which is also pretty gross. And so it's very, very addictive. And I'm sure you guys know that. I will say this is the number one reason not to smoke, because in addition to being addictive and a stimulant, it can have very severe consequences on your cardiovascular health. The nicotine, when you get that nicotine in your body repeatedly, it can cause damage to your heart. So again, don't smoke, and if you do smoke, try to find a way to quit. And then nicotine, by the way, is one of just many, many compounds that are bad for you when you smoke. It's just the one that gets you addicted. All right, so this scopolamine, this is a compound. This is also in the nightshade plant. I looked this up. There are things that are called angel trumpet, like trumpet vines. Those are different. This angel's trumpet is sometimes called devil's trumpet. It is a particular subspecies of nightshade. It fits in that nightshade family, and it contains this compound. And this compound, when extracted, can be used for medicinal purposes. It can be used to treat nausea and other kinds of motion sickness and that kind of thing. So again, you probably don't want to go chew up a plant to ease your nausea. You probably want to get it extracted and used in like a patch or something. All right, so histamine. I am currently having a very personal relationship with my histamine. Histamine is this. All right, so it is based on one of those heterocycles that we saw earlier. It has this group on it, and so this it is a basic compound, but it is used in your body. It's used as a way to communicate between other different parts of your body. It's used as I don't know that it's a neurotransmitter, but it is used as a way to communicate between different parts of your body to tell your body to have certain physiological effects. Now, when you have these effects, it can do stuff like make you sneeze. And I have paused making this video about 5 times so that I could sneeze uncontrollably. It's just one of those things. I get allergies 3 times a year, and it lasts 6 months each time. It's no fun. And if you're wondering, that's 18 months a year that I get allergies. All right. In any case, if you can come up with ways to counter some of the unpleasant side effects of the histamines, then you can reduce some of your symptoms from those allergies or those responses that your body has. And so we can use things that are called antihistamines. And this is just, these are a couple of examples. This one, the fexofenadine. Fexofenadine is sold in the United States as Allegra. And so this is a commonly used over-the-counter medicine that's used. There are others that are related to this. This one is used as an anti-ulcer drug. This one's been around for quite a while. It was invented in the 70s, and it still finds some use for treating acid. Not so much the acid reflux, but lowering the amount of acid in your stomach and decreasing the risk of ulcers. So it's sold under the name Tagamet, or Tagamet, not Tagament, Tagamet. All right, and then we're going to get to some kind of interesting ones, and I will just mention this right out that some of these are naturally occurring neurotransmitters, and some of these are very addictive drugs. And you'll notice that there are some very close similarities. And this is part of what makes some of these drugs so dangerous, is that they mimic some of your neurotransmitters and cause your brain to cause your nervous system to perhaps release certain neurotransmitters or stop releasing certain neurotransmitters, which may give you a certain sensation. It may cause you to have a high or a low. It may make you feel really awake or make you feel really sleepy, depending on what kind of medicine it is. So many of them are based on this simple structure where we have a benzene ring, CH2, CH2, NH2, which is the phenethylamine or phenylethylamine. All right. This one is adrenaline. And so you'll see adrenaline here, epinephrine. This one is naturally occurring. And then this one is the noradrenaline or norepinephrine. This is a neurotransmitter, increases heart rate, dilates air passages. But this is an important part of your nervous system. Using these chemicals makes your body do things, and I don't know the full range of those things, but that is the norepinephrine. Down here, this one is methamphetamine. Again, you'll see it's that same structure. That methamphetamine is a very addictive drug. It's sold as either speed, meth, crystal meth. You've heard of it. Again, I'll say don't do drugs. All right. This one is mescaline, which is isolated from peyote. All right. But you'll notice that all of these have the phenyl group, an ethyl, and then a nitrogen. And just changing little things on there can change it from one thing to another. For example, changing this, getting rid of this methyl makes it just amphetamine. And so there are some pretty potent drugs and some that are not as potent. And there are also some very useful medicines that are derived from these that can be used as heart medications, allergy medications, any number of things. All right. Dopamine is a neurotransmitter. You'll see that dopamine is very closely related. I'm going to go back here. Very closely related to the norepinephrine. Right here, you'll notice there's a hydroxy group. Dopamine doesn't have that particular hydroxy group, so that's the main difference there. So it is a neurotransmitter that's used by your brain to communicate from one cell to another. It does all kinds of important things. Helps you process movement, emotions, any number of things. If you stop producing the dopamine or you don't get adequate dopamine production, that's going to be some of our symptomatic diseases, including Parkinson's disease and any number of other ones. So dopamine it's a very critical neurotransmitter in your mental health. And so having proper dopamine levels is important. All right, there are a couple of others. Serotonin, which is somewhat related, although a little bit different. All right. This is the fluoxetine, which is sold under the brand name Prozac. It is one of many serotonin reuptake inhibitors, SSRI, so the selective serotonin reuptake inhibitors, which has really revolutionized psychiatric medicine. So it's made it possible for people to treat severe depression and anxiety. And then here we'll throw in a couple of other potent psychedelics drugs. These are hallucinogens. One that is isolated from a particular type of toad, and then this other one is derived from mushrooms. So let's look at number 5, and we'll go through we'll kind of finish off our list of dangerous drugs to look at. All right, so LSD and codeine, and you'll notice these have different effects. This one is a hallucinogen, and this one is a narcotic, but they both have the 2-phenylethanamine, and this is the 2-phenylethanamine. I put it there for purposes of this. What we want to do is we want to identify the atoms of the 2-phenylethanamine that are in each of these. And so while these have very different effects, they are related to each other in some of their structure. So I'm going to use this numbering. All right, so the carbon that is attached to the nitrogen, I'm going to call 1, 2, and then we'll do 3 and count out around the ring through 8. So those particular 8 carbons I'm going to number. And so here we've got a phenyl group, carbon, carbon, nitrogen. So this is 1, 2, 3, 4, 5, 6, 7, 8. And so that is the phenylethanamine that is part of LSD. Now, all these other things make a huge difference. I mean, this and this would have very different effects in your body, as does this, which also contains that phenylethanamine. So here we've got 1, 2 carbons, and there's the phenyl group, and there's the nitrogen. So we'll do 1, 2, 3, 4, 5, 6, 7, 8. And so, again, both of these have very dramatic effects on your brain chemistry. All right. So we are going to end it here. And in the next section, we're going to look at how do we prepare amines? Like what are some methods for preparing amines? And there's some pretty cool stuff. So stay tuned for that next video.